All right. Hello, and thank you for coming. So, my name is Mattsi. I'm a software consultant from Codurance, and I've been studying Rust for the past year and a bit. I'm going to talk to you a bit about Rust. So, Rust is seeing a huge spike in interest in recent years, but most developers don't actually know a lot about it despite its popularity. So this talk is going to introduce what Rust is, what it is good for, what it is not so good for. It's going to teach you about some of the key concepts in Rust that really differentiate it from other languages. And finally, I'll share some resources for further study if it interests you and you want to take your studies further. And I'll leave a bit of space at the end for questions, but please feel free to leave any questions in, I think there's like a Q&A feature here and a chat feature. So if you leave any questions and hop in, I'll get to them at the end. So what is Rust? Rust is a compiled systems programming language with a focus on performance, security, and safety. The best way to explain Rust is by comparison to existing languages you may already know. And that often comes down to a discussion of high level versus low level programming languages. So, what I mean by that is that the high level languages tend to have more sort of guardrails, making it a bit safer, giving you more confidence. But that comes at a sacrifice of control and performance. And up here, we're looking at, Scratch, if you know of that, is a really, really high level language that's just kind of used for teaching newcomers into programming. And then at the opposite end of the scale, you have assembly being really, really low level, giving you very little kind of, as I say, guardrails, no kind of assurances, but giving you a lot of control and performance. And then C and C++ are up here, a bit more guarantee, but still very, very low level. Um, so when we say Rust is a systems programming language, we're referring to low-level programming of systems that other software depend on, such as operating systems, drivers, databases. These are domains that higher-level languages like Python and Java may not be appropriate for, but things like C++ and Rust certainly are, and this is where you find Rust in this bracket. So you can think of it broadly more as a competitor to C and C++, and not so much as of a competitor to C Sharp, Python, Java, so forth. It's a multi-paradigm language. Oh, sorry, no, I've missed one of my notes there. I wanted to also point out that while this is true, Rust is not exclusively for systems programming. So you can do anything with it that you would with any other language. And the language designers, they go out of their way to point out that Rust is intended to empower developers, that they want people to program with more confidence and safety and to program in a greater variety of domains. So it's not that you can only program low-level things with Rust. There's all sorts you can do with it. So it's a multi-paradigm language, and by this what I mean is that Rust has some functional features, but it isn't necessarily a functional language. And similarly, it has some object-oriented features, but not enough that you would really call it an object-oriented language. It dips its toes in different sort of schools of thought. And Rust is not garbage collected. This is probably the biggest factor that makes it much more performant than higher level languages. Traditionally, the choice between lower level and higher level languages was framed as the choice between no memory safety but high performance. So that would be C and C++, and having guaranteed memory safety, so avoiding a whole class of possible problems and errors and vulnerabilities by having garbage collection, but being lower performance as a result. Rust tries to break this mold by offering guaranteed memory safety through a system called the ownership rules, while also being as performant as C and C++ because it does not have garbage collection. All right, let's talk about the features that make up Rust. So Rust performance is comparable to C, as I said. In some benchmarks, it will win. In some benchmarks, it will lose. But it's in the same ballpark. It is not garbage collected. It uses the ownership rules I referred to. We'll get to that a bit later. Rust has a really strong type system. It also makes a lot of use of inference, so you don't always need to annotate every variable type. But despite that, it has a really strong type system that tries to make your life easier and safer. In general, this is part of a pattern you'll notice in Rust, that the language designers are trying to move as many errors that would occur in runtime. They're trying to move that to compile time instead. So they're sort of front-loading that complexity. So rather than the user getting hit with errors and bugs, you'll kind of hit with these errors and bugs up front, and you need to tackle and handle them as soon as possible. And it sort of makes development a bit more cumbersome, a bit more complex, but it prevents what would have been costly later down the line, handling and resolving bugs that would have occurred but now won't occur. That's sort of a big part, I think, of the philosophy behind Rust. So Rust has a number of systems programming features as well. So it allows direct memory manipulation and interoperates with other compiled languages like C. It features safe concurrency, so the same ownership rules we were discussing before. They also prevent a number of concurrency errors, such as data races, so you can more confidently use concurrency and multi-threading. Rust has a very comprehensive set of built-in tooling as well. It creates a really painless development experience. So what might you use Rust for? What are good applications of this tool? I would say it's a good use case for anywhere where performance and safety are key considerations, such as game engines, operating systems, file systems, web browsers, simulations, embedded devices and firmware, drivers. I've also included safety critical software, which I think is an important one. So if you're working with something that a piece of software that can actually harm people, that can cause human cost, if something goes wrong, then you really want a tool that has a lot of guarantees, a lot of safety. It can give you a lot of confidence that your program is correct, and Rust is a really good use case of those. So what are we actually talking about? What actually is Rust? What does it look like? Well, it looks a little bit like this. You'll probably notice pretty quickly that it looks a lot like other C-like languages. So it looks similar to Python, Java, C#, JavaScript. You've got your imports at the top. You've got functions. You've got nested scope denoted by curly braces. You've got parameters denoted by round braces. It should be pretty similar. It's pretty intuitive. You've got sort of static methods, or they're not called static methods in Rust, but yeah, you've got static methods. And this is an implementation of the guessing game in Rust. So there's a couple of interesting bits here. We're reading in from the terminal. And in other languages, when you handle an error here, you might have an exception and have to try catch that exception. But Rust instead uses types to enforce error safety. So what we're doing here is a little bit more like the optionals in Java, if you've ever used those. I think Kotlin has the same as well. So the result from this read line is a type that needs to be handled in some way to ensure that error is checked. And you can't not check that error, basically. The type system will enforce it. We're also seeing some pattern matching, which is quite cool. So when the user has a guess, we need to decide, does this guess match what we expect? Is it greater or lower? And then respond to that. And we're able to just say, okay, if it's this, do this. If it's that, do that. If it's this, do this. This is a really powerful pattern that comes up a lot in Rust. It looks very simple in this example, but it can have quite interesting implications. A lot of the time in Rust, you're kind of making state machines and looking very directly at, okay, if the state of the system is this, then do this, otherwise do this, and pattern matching really enables this pattern of development. Now let's look at the features of Rust. So I mentioned earlier that Rust has great safety and security, and this is part of how Rust achieves that. One really neat feature is that all Rust strings are valid Unicode sequences. So in many languages, encoding errors will occur because the default encoding will be ASCII. And to support Unicode, which is a very common problem, then you have to transfer between different encodings and keep track of all these different encodings and make sure you're in the right state at the right time and whatnot. And Rust avoids this problem by making UTF-8 Unicode the default. It also has a number of features that guarantee memory safety. The Microsoft Security Response Center, about 70% of the vulnerabilities they report every year are memory safety issues. So these are things like, say, a program could be tricked into freeing a space of memory twice, which creates undefined behavior that can lead to malicious problems, or could be tricked into changing a pointer in memory to point at a different space in memory, and that can lead to a malicious actor getting access to a space in memory they shouldn't have access to. So a huge number of issues such as these are prevented by using Rust. In some cases, C and C++ can even suffer memory vulnerabilities from really simple things like overflowing an array. And this is somewhere where Rust just caps off and says, nope, if you overflow an array, that's an immediate halt and end execution. That's a serious problem. Whereas in C++, I believe it's undefined behavior. And there are a number of, this is one example where there's a number of areas like this where Rust tries to add more security and safety with sort of common sense changes, really. If you have written much Java or other C-like languages, you'll be glad to hear that Rust has no nulls whatsoever, and that means no null pointer exceptions. Null pointer exceptions are called the billion-dollar mistake. They are the most common error in just about any language that supports implicit nulls. And many new programming languages are solving this problem by just not allowing nulls whatsoever, and Rust is one of them. Rust also has no exceptions and no catches. You can't try catch anything. The closest equivalent to an exception that it has is panic. So you can say panic and it will immediately halt execution safely and cleanly. But this is really only intended for rare situations. You can use it in testing where, halting the program is fine. You can sometimes use it in libraries if the consumer is using your library wrong and forces you into an invalid state. But generally in production software, you should not use it. What we do instead is to use the type system and the optionals that I was talking about earlier. More specifically in Rust, they're called option and result. So a result will check whether the result of a function is a valid result, or in other words, it's okay, or if it's in an error state. So for example, here we're accessing a file in the file system, but we can't know for sure that it actually exists. It's really there, in which case there could be an error in which the operating system says this doesn't exist. And we check for that by saying, okay, if it's okay, then get the file, do what we want. If it's an error, then handle the error. And the interesting thing here is that this variable file is impossible to access until we've done this check. If it's in an error state, you cannot access the file whatsoever. So this variable that might not be defined, you can't use it until you've proven that it is defined. So it completely avoids that whole possibility of trying to access something that isn't actually there. I mentioned the ownership model a bit earlier. So the ownership model really differentiates Rust, but it is very, very simple to understand. The ownership rules are just that every value in memory is linked to a single variable, and that variable owns that value. There can only be one owner of a value at any given time, and when that owner goes out of scope, the value will be dropped. And when I say dropped, I mean, erased from memory, gone, freed up, no longer accessible. So as an example, here we have a function that is creating a new value. So it's creating a string that just says hello, and this will be stored in memory somewhere. then we immediately return that string. So if you omit a semicolon in the last line on Rust, that is a return statement. So we're returning this string, and the value of that string is then assigned to this new variable we're creating here, s1. Call the function creates the value, we get the value and assign it here. And in this scope, if this wasn't returned, if we didn't return this value here, the compiler would automatically add something to the end here to say, okay, drop some string value. So in C++, you manually need to do this and check that you're releasing your memory. But in Rust, it will just automatically add this and say, okay, this value is no longer owned by anything, therefore it's not in use. Therefore, I'll add an extra line here that just makes sure it gets cleaned up and erased. But in this case, we are returning it, so it's kept. This space in memory continues to be occupied and is moved over here. And that same sort of statement we're imagining over here will actually be added by the compiler over here instead, because this is not returned from this function. So its scope ends here, and it's erased as soon as it leaves scope. We also create this variable here. So we're creating a value in memory, the hello string again, and assigning it to s2. And then we can pass it to this function, which takes and gives back ownership. So by moving this value or moving this variable into this parameter, this new variable, which is a parameter of this function, takes ownership of that value. So it now owns a value and then immediately returns it. And that value then gets assigned to this variable. So the S3 variable then owns that value, which means that S2 does not own it and now cannot use it. So for example, if over here we try to assign S2 to a new variable, it actually comes up with an error and tells you, no, you can't do that. That's illegal. Essentially because now that the ownership is moved, if we then tried to modify that value in memory from here, then it might not be there and that could create an error. Or we could end up modifying it from two different scopes, and the scope where it is owned might assume that it exists in one state, not knowing that it's being changed into a different state by some other piece of code that it's unaware of. So this ownership model really simplifies things and avoids all sorts of problems. And if I give you a look at the editor over the compiler, we can see it gives us really, really helpful error messages. Here it's saying, okay, here is the exact line where a problem occurs. You're trying to use a value here that's been moved. And then it shows you where the move occurs as well. So it's saying value moved here. It's saying, look at this variable passed into this function. A move has occurred here. You've moved the ownership of this value. And then you're trying to use this variable after it's been moved, and you can't do that. So really, really helpful tooling that tries to simplify the ownership model and make it easier to handle and understand. Now, another really interesting feature, they have algebraic data types similar to F# or Haskell. So you have an enum that has variants. Different variants can have different values, and this all feeds into the pattern matching I was discussing earlier, and how you can sort of railroad your program down different paths depending on the state in a really clean, readable way. The pattern matching in Rust is very powerful, so you have a number of neat features, like, say, you can use an OR. In this example, we're pattern matching on strings, and we're saying, okay, does this variable match this string or that string, then do this. You can also do ranges, select 1 to 5, and you can apply ranges to letters, like saying if it's between A and L. And there's a lot of other neat features that pattern matching has. It's really powerful. And the most interesting feature is that a pattern match must be exhaustive. So the compiler actually enforces that you must account for every possible state. And that has some really interesting implications, because if you create an enum that manages the different possible states your system can exist in, you write a match statement somewhere that relies on that enum, and then later you add a new state by adding a new variant to that enum, so a new state that your system can exist in. The compiler will pop up a warning or an error and will tell you, hey, this match statement over here doesn't account for this new state you've added. So it prevents the error in which you might forget about that statement altogether and not realize that you've created undefined behavior because this new state you've created isn't being handled by this other piece of code. The compiler will alert you to this error. It doesn't have object orientation, like I said, no inheritance, but it does have interfaces. I'll gloss over that pretty quickly because we're low on time. So what is the future? Is the future Rust? Maybe, I kind of hope so. Rust has been the #1 most loved programming language in the Stack Overflow developer survey every year since 2016. And that's huge, that's really crazy. Actual adoption from companies is much lower, of course. So the developers might be really keen on Rust, but companies are slower to adopt it, and hopefully we'll see change of that over time. It's hard to say. Rust has its own foundation now, so it's no longer managed by Mozilla. There's a whole foundation that involves sponsors from various different big companies who are working together to ensure the future of Rust and to actively develop the language. And there's an ongoing project supported by Google who are trying to add support for Rust to the Linux kernel project. So this would be the first language other than C in, I think, how old is it? About 30 years that has ever been supported in the Linux kernel. And I think that's a really strong endorsement for Rust, just knowing that all these really expert, low-level engineers that we trust with the Linux kernel, which is used by billions of devices across the world, is a really, really vital piece of software where they put their trust in Rust and feel like this is something interesting worth trying. It hasn't been added yet, but that proposal is well underway, and it looks like it may well happen, which would be really exciting. And Edward Snowden has endorsed Rust as well because of the security features we discussed earlier. He wants to see more people using it to prevent various types of bugs that can lead to security vulnerabilities. It wouldn't be fair if I talked about these advantages and all this good stuff about Rust without also talking about some of the disadvantages. So one is that Rust has a very young community. It's not as well established as other languages. And this has a couple problems. One is that it hasn't built up a kind of extensive big library of open source software that some things like Java and Python have. It does have a very active, strong ecosystem, but you can't say it's on the same scale as one like Java that's been around for much longer, of course. And there's also many fewer jobs in the market, or no, sorry, the other way around. There are, but there's many fewer developers in the market, was what I was trying to say. So if your company wanted to build their next system in Rust, that's something you'd have to seriously consider, is are we going to be able to get enough Rust developers to support this? If the people who move on, how are we going to replace them? How expensive and difficult is it going to be to actually get experienced Rust developers? It's also more complex than other languages, so it's easier to train people in languages like JavaScript, Python, Ruby, than it is to train them in Rust. Rust sort of front loads a lot of complexity up front, a lot of the sort of errors and problems you might reach later on, coming back to you in bug tickets. Rust tries to make you face up to these up front and prevent those bugs, but that does make development more complex. It does make the language more complex, and not every case needs that level of complexity, and that's fine. So in some cases, you might just want to create a quick web app and you don't want all this safety and security, and that's a totally valid decision in itself. So if I have piqued your interest, if you're really keen to let's go learn some Rust, then I can recommend the Rust book as the sort of best starting place to get introduced to the language and give it a try. This is available for free online. It's open source. It's written by the language designers themselves. And it's very frequently updated. It's really well written. It's also available on paperback as the Rust programming language. But learning, reading, studying a language is only part of a problem. An equally big, if not greater problem is actually getting practice in. And for that, I really recommend using Exercism. They have this Rust track, which has all sorts of different programming challenges you can complete in Rust. And they also, this is the thing that really makes Exercism stand out to me. They have these volunteer mentors who will come on and give you advice on your solutions. So, for example, here I've solved a problem in Rust, and Bob, who is a really, really nice guy, does a lot of volunteering and Rust mentoring. He's come along and given me a bunch of advice around my solution, around how it could be better. And you can see from just how much he's written, he's even benchmarked my code for me. It's just really, really, really valuable feedback. So definitely Exorcism is a fantastic tool. You could also start a study group, which is how I got into Rust. And if you're more of a video listener or video learner, there's a channel on YouTube called Let's Get Rusty, which has lots of interesting, good introductions to Rust. And I recommend giving the Discord Rust groups a go. I found them really, really useful for just quickly jumping on and finding someone to help me with some problem or other I'm having. Whew. All right, that's all from me on this presentation. My socials are down here if you want to follow, or if you have any questions you want to reach out about. If I don't get time to tackle them here, then feel free to reach out. And I said I would leave some time for questions. We've got a few minutes. Let's see. Oh, thank you for linking to the Rust book. Yep, that's right. That's exactly the right one. And yeah, Rust for Rustaceans is the kind of more intermediate book that I'm actually reading right now, and that is a really good follow-up from the Rust book. So what questions have we got in the comments? When the variable scope ends, is it fully deallocated from memory? I would say ostensibly yes. It's probably a bit more complicated than that. I wouldn't be surprised if there's some lower level implementation details I don't know about. But the broad assumption you can make is that yes, it'll be deallocated right away. There might be some form of caching or grouping these deallocations together. You know, there might be another level where it's sort of trying to improve efficiency by grouping some of these deallocations. But as far as I'm aware, it's just deallocated immediately. Is this garbage collection? The broad consensus is no. This isn't the same thing as garbage collection because you don't have a sort of active thing running at runtime doing it for you. It's just part of the program. The compiled program has these instructions embedded in it at compile time. I think you can say it's similar, but I don't think it's quite the same. Am I working professionally in Rust? No, unfortunately, I'm not. I have been studying Rust mostly in my spare time, along with a group of colleagues in a study group over the past year or so. I started the group back in January last year. But no, I haven't had a chance to work professionally in it. There are companies out there doing it. I've heard of several of them. We almost had a contract. I work for a consultancy. We almost had a contract with one of them a while back, but it didn't quite work out. What is the best way of running? Okay, so I think I've answered the one about learning Rust. Info, no worries. Any big games written in Rust? Yes, that's a good question. There are some interesting Rust games. I think there's actually Rust game development. There's like a website out there somewhere that tracks all of them. And there's one in particular that is pretty big. Which one was it again? I forget it. Oh, is it called Valor something? Games. Okay. So where would you call it? Maybe it's under open world. Valoran, that's the one I was thinking of. This is like a really big game project written in Rust that's becoming pretty big and has lots of support. I think this is probably the biggest known sort of Rust game, but there's a whole community out there doing Rust game development, and it's definitely happening. Is there a demand for Rust developers in the sector? That's a really good question. I'm not necessarily the right person to really be answering that, but I can tell you that there's all sorts of opportunities out there and people trying to find. Is this the one? Yeah. So there's things like rustjobs.dev. It is working to collate different companies that are hiring Rust. And a lot of it, that's the funny thing I found, a lot of Rust jobs right now seem to be in blockchain. For whatever reason, there's a lot of blockchain people. You also got security companies like 1Password that are using Rust for obvious reasons. So definitely jobs are out there. I've known friends and colleagues who have worked in Rust. It does exist. There's definitely Rust opportunities in London. But I would be lying if I said that it wasn't more rare and more difficult to get into than other languages.